Hello, guys. Welcome back to Maths Zone African Motives. We are still on our electrotechnics N4. And in this case, we are going to actually have just a recap on our magnetism. I'm not going to dwell much into that. We just need to add other questions, all right? Just to add one or two questions. What happens here is that we dealt with this one in our N3, all right? Electrotechnology N3. So I'm going to put that video in the playlist, in the same playlist for N4, so that you watch the video on the magnetism, all the basics, and actually everything that is important. All right. So make sure that you go through the video. So in this case, I'm just going to recap the formulas and work out just one or two questions. All right. Remember, we were referring to magnetism as the force exerted by magnets when they attract or repel each other. So we are saying here it is simply is the force exerted, all right, by what? By magnets. By magnets when they attract or repel. So they can attract or they can what? They can repel each other. So that is the condition that you're going to have. Also, like I said, if you have to go through that video, I've explained everything about the magnetic field, this and that, everything that you need to understand in your revisions. All right. So just go through, understand everything about the magnetic lines, the magnetic flux density in terms of the definitions. All right. So I'm just going to quickly just recap the formulas. Remember it, the formulas on the magnetic flux, all right, which is given by what? By phi. So this is phi. I don't know how do you pronounce it, guys, but that is for magnetic what? Flux, which is measured in what? In Webers. So it is actually the measure of total magnetic field that possesses through a given surface, So for that surface, you are going to need the area of that. So that is the magnetic flux is given by magnetic flux density times what? Times area, which is measured in what? In Webers. That is something called like Webers. All right. So that is the magnetic flux, all right, which is taken from the magnetic flux density and what? And area. Then we have the magnetic flux density. Definitely, we're just going to make it the subject of the formula, the magnetic flux density. So like I said, this is just a recap on the formulas, but go through the theory part and everything on the N3 video. So here just make B the subject. That's going to be magnetic flux over what? Over area. And this is measured in what? In Tesla, which you can write T, Tesla. All right. So that is what you are going to actually need or to have in your calculations. All right. So we said A is for what? For the area, the cross-sectional area in square meters. All right. Then definitely you talk about what? The magnetic what? The magnetic flux in what? In Webers. Then the magnetic what? Magnetic flux density. All right. Magnetic flux density, which is measured in what? In Tesla. You can write T for that. So that is what you're going to have. Then another aspect that we referred to was on the force on a conductor. All right. You can have a condition where you are calculating the force on the conductor. All right. The force exerted on a current carrying conductor. placed in a what? In a magnetic field. All right, so that is another aspect. The force on a conductor, that is on a current carrying conductor, on a current carrying conductor through what? That is placed in a magnetic field. So the force is given by the formula, that's B times I, the current, times L, the length, times the sine of theta. So this is an adjustment that I want you to make on your formulas, all right, from the formula sheet. If you are to check, these are the formulas that you're going to use in your magnetism and electromagnetism from 11. All this part is about what? Magnetism and electromagnetism. So if you check, this is the formula for the force that you're given here, but they are not having the sine of theta. So you must know that you've got what? The sine of theta, the angle that the conductor makes with the magnetic field, the angle that the conductor makes with what? The magnetic field. So you must have it here. Even on this one, you're going to see this formula later on. We must have also the sine of theta on this one. So these are the adjustments that you must make. All right, so that is what we are going to have. We have already talked about B, our magnetic flux density, and our I there is the current. So I is just our current, which is the current flowing through the conductor in amperes. The current flowing through what? The conductor. Then the small letter L is for the length of the conductor. This is the length of what? Of the conductor in meters. Then theta is the angle that the conductor makes with what? Magnetic field. That is our angle, that one in what? In degrees. So it might be in degrees. All right. The angle that the conductor makes with the magnetic field. So all that part, go through it. This is the force which is measured in what? In newtons. All right. So that is like I said, we can calculate that force. So I want you to also go through the effect of the force due to the right hand rule, the left hand rule, all right, from the motor rule, the Fleming's motor rule, all right. I explained that one in your N3, so please go through that. The direction of force can be reversed, reversing the direction of the magnetic field, reversing the direction of the current through the conductor can affect what? The force, the direction of what? Of the force. So that is the part of your N3. So I want you to go through that. But as part of your calculations, let us just add also the magnetomotive force. All right. We have also the MMF, which is the magnetomotive what? Magnetomotive force. MMF. All right. So that is simply the work done in moving the unit magnetic pole once around the magnetic what? Circuit. So that MMF, which is our magnetomotive force, is simply the number of turns times what? Times current. Number of turns times what? Times current. So it is measured in ampere turn. Ampere 10 or tens, which is 80 amperes times what? The tens, number of tens. So that is what you're going to have. So like I said, I there is what for the current, but we wrote it before. We have I there. It is about N. So that's the number of what? The number of tens. Okay. We also have the magnetic field strength. All right. All this you are given. All right. All this, the MMF, you can make it from this one. You can obtain it from here to say these two, they're equal in terms of exam. So that's where you can take what? Your magnetomotive force. All right. Or you can take it from H, because H is equal to MMF over what? Over the length. So this one represents the magnetomotive force. As we can see, we are not directly given the formula. All right. So that's another aspect, very, very important. And another formula is for the magnetic field strength. You're also given that magnetic field strength. You have this formula which is represented by what? By H. So that's our magnetic field strength is equal to the magnetomotive force over the length. It is actually the ratio, the magnetomotive force per the magnetomotive force per what? Per unit length, per unit length, magnetomotive force. And that magnetomotive force, remember, it is what? Number of turns times current. So you can simply use that over what? Over the length. All right, we have talked about everything that we have here. So this is measured in ampere per what? Per meter. Ampere turn per meter, or you can just write amps per what? Per meter. The length measured in what? In meters. Then the last one that I want us to consider, not to say these are the only formulas, all right, but just all right, let me see. Magnetic reluctance. So the reluctance, also you are given this formula for reluctance. So reluctance is represented by the letter S, all right, which is the ratio of the MMF to the magnetic flux, magnetomotive force to the magnetic flux. So therefore, S is equal to MMF over what? The magnetic flux. So it is going to be measured in ampere per watt per web per unit of the magnetic what? The magnetic flux. So that is what you're going to have, guys. We have explained all of these terms, presentations. Then also maybe sometimes you might be given to calculate power, given force and velocity. Remember, from our science, power is what? Force times velocity. And also conversions of units from square millimeters, mostly in terms of area. You need to convert it to square meters. You multiply by 10 to the exponent of what? -6. You have square meters, square centimeters to square meters multiplied by 10 to the exponent of what? -4. So the vice versa, you multiply by positive if you want to convert to the other unit. All right. So basically, that is what you're going to need. And like I said, all the notes, explanations of the theory is in our N3. And please do watch the videos. I'm going to place them in the playlist. So let us quickly go through this information with what we have. These are the typical questions. A magnetic flux of 55 milliwebers, all right, according to what we are given. We have got the magnetic flux 55 milliwebers and produces a magnetic flux density of 1.75. So we have got the magnetic flux density 1.75 Tesla. In the air gap between two magnetic poles, calculate the area of what? Of this trip gap. So what is the area? All right, this is just playing around with a formula. As the formulas that we have, we can use the relationship between what? Magnetic flux and flux density, any of these two. All right, according to your formula sheet, the one that you're given is magnetic flux density in terms of this. So simply make area the subject. All right, so simply divide by what? By this. So it's going to be magnetic flux over what? Magnetic flux density. You have your what? Your area. And that's the idea there. So our area is going to be what? Magnetic flux over magnetic flux density from what we saw from our change of subject. So we have got this and this. All right, 55 times 10 to the exponent of -3, the milliweber there, over 1.75. So that was going to give us 0.0314. All right, in square meters. The area is going to be in what? In square meters. Take note of the units. All right, so that is the basic approach of how we can be given this. All right, let us move on to another one where we are given a conductor with a length in millimeters. So convert this to meters. Simply divide by what? 1000. That's 0.47 meters. Moves at a constant velocity at right angles. So the angle is what? 90 degrees. That is at what? At right angles. The angle that the conductor makes with what? The magnetic field. With a uniform magnetic flux density of, we are given the magnetic flux density of 0.95 Tesla. Calculate the magnitude of what? The force exerted on the conductor. If a current of what? 6.8 amps passes through the conductor, calculate the magnitude of the force. So what we need is the force. The force on a conductor. From what we had, the force can be determined. Remember, we've got this formula for the force on a conductor. So you can simply apply that formula. Force is equal to BIL times what? Sine of theta, or BLI. All right, where we have got everything in this case. We've got everything. Our magnetic flux density 0.95, current 6.8 times the sine of theta, which is our theta. I left something here. I left the length. The length 0.47 times the sine of what? Our theta is 90 degrees. So that is going to give us the force. Just like that. And that was going to be 3,036 Newton. Remember, the force is measured in what? In newtons. So you see, basic questions, actually, that is what you're going to have. So do not panic on magnetism and electromagnetism, guys. It's nothing. We are going to see that it is just our N3 as it is. All right, a coil on number 2. We've got 2 questions, 2 and 3, that we are going to also consider. Number 2, a coil has got 1,250 turns. Number of turns 1,250. All right, is energized by an exciting current of what? 1,5. All right, 1,5 amps. The coil produces a magnetic circuit of length, right? The length in centimeters, so divide by 100. 1 meter is what? 100 centimeters. So that was going to give us 0.135 meters. Calculate the magnetic field strength of the system. The magnetic field strength is represented by the letter what? The letter H. So what is the magnetic field strength of the system? From what we have, we can use this formula, magnetomotive force over what? Over the length. But remembering that the magnetomotive force here represents what? Represents the turns times current, Ni over length. So we can simply use that. So N, we have it, times the current, 1,5, over the length, 0.135. So that is it. This was going to give us 13,888,889. And it's amperes per meter per unit of the length. Amperes per what? Per meter. So you see, guys, how the questions can be given as. Apply your formulas as they are. All right. According to number 3, calculate the what? The reluctance. So that's our S. The reluctance of a magnetic circuit in which a magnetomotive force, already we are given the magnetomotive force, MMF is what? 2,200 ampere turns, produces a magnetic flux of, so the magnetic flux is also given 62 milliwebers. Calculate the reluctance S. So reluctance S is given by which formula? Our reluctance can be taken from the magnetomotive force over the magnetic flux. So it's direct. We have the two, guys. So we can simply use our formula direct as it is. We have the magnetomotive force 2200 over what? 62 milliwebers times 10 to the exponent of minus 3 to get rid of that milli. So that's our reluctance 35,483,871 in ampere per watt per unit of the flux. So it's ampere per watt per Weber. That's how these questions can actually be given as. So we shall proceed looking into other aspects. Just follow the playlist so that you understand the questions and also everything that you need to know on this topic. All right, follow up to the end. But for now, that is it till we meet again.